Yeah, thank you very much for this kind introduction. Thank you all for coming. It's very nice to be here in Berlin and in this community. I got into machine learning causality through an interest in neuroscience 20 years, a bit more than 20 years ago. I never lost that interest, even though I went to the more formal side of things, but it's very exciting to see how things are converging again. So I want to start, and it's also interesting. I saw most of Ananda's talk this morning, so you'll find that we're interested in some of the same things, even though maybe he didn't use the word causality, and I'm going to talk mostly about causality, but in the end we'll end up talking about similar kinds of models probably. So you all know that we, as the community, think that we can perform object recognition at human level performance. And it was interesting to see this previous talk that made some very good points about what's different between internet-style object recognition and human object recognition. So we think we can do that well. We can robustly recognize these cows. But then people have found out some hand-picked examples of cows that surprisingly we cannot recognize with machine learning systems. And these are examples, in this case, where the cows are standing on the beach. And of course, one of the ways to think about that is that these cows, it's probably the case that in the training set, most of the cows that were there did not stand on the beach. Maybe none of them stood on the beach, but they were mostly on green meadows, etc. And in an IID scenario, which is what we're usually obsessed with in machine learning, so independent, identically distributed data, if it's the case that the cows in the training set are predominantly on green pasture, then it's perfectly reasonable for a machine learning system to use these green meadows as a feature when deciding whether something is a cow. So this kind of robustness with respect to putting objects into different contexts, this is not built in if we ask a system to perform well in an IID setting. And that's why these cows are not recognized as cows. So in other words, we could basically summarize this as saying machine learning uses correlations or statistical dependencies rather than causality. And in a maybe even more extreme way, this shows up in the recent phenomenon of adversarial vulnerability. So these machine learning systems, they are so highly optimized with respect to a given IID training set that they are not robust with respect to even tiny violations of this IID assumption. So in this case, if people add a little bit of malicious noise to a test image, imperceptible to humans, so the image looks the same after adding the noise, then the system may certainly classify this little pig as an airliner. I think you're all aware of this. And maybe as a last example of a difference between machine learning and causality is this shopping example here, which also shows that this IID assumption is not innocuous. In this example, we are shopping for a laptop rucksack, and then the shop, and I should say this is already at least 5 years old, so it doesn't work anymore, this example. The systems are continuously being improved. But in this case, you shop for a laptop rucksack, and then the shop recommends you should buy a laptop to go along with this rucksack. And this is slightly funny for us because intuitively we would think that buying the laptop or owning the laptop is a cause for wanting a rucksack in the first place. And buying the rucksack then is just an effect. But of course, both of the two things contain information about each other. So the cause contains information about the effect because it controls the effect. And the effect contains information about the cause because it carries a footprint of the cause. And this information, if we measure it in terms of mutual information, it's symmetric. So it's the same number. But obviously, the causality is not symmetric. So there's a fundamental difference there, and this difference becomes important once we intervene in a system by recommending an item. Because if we intervene on the cause, the effect will change. But if we intervene on the effect, the cause will not change. So there's a deep asymmetry, a difference between correlation and causality. But of course, there are links between correlation and causality, and these were first understood by this gentleman here, who at some point was a professor in Berlin, Hans Reichenbach, very interesting character, who did his PhD on foundations of probability theory, didn't find an advisor who would give him a PhD for it. Eventually it worked, and then very fast he was hired to the physics department in Berlin by Planck, von Laue, and Einstein. Had to leave in 1938, went to Turkey, and later went to America, where he was, for instance, the PhD advisor of Hilary Putnam. So Reichenbach said that if we find two observables to be dependent, then there is a causal explanation for this. There must be something else that causally influences both of them. So no statistical dependence without causality. And moreover, he said we can choose this third one such that it screens X and Y from each other, so that conditioned on Z, the other two became independent. So the third one explains all the dependence there is. So if we look at so there's three possible explanations to correlated quantities that can be caused. So they're, in the generic case, they're caused by this confounder Z, and this confounder could coincide with either X or Y. So if we find the frequency of storks and the human birth rate to be correlated, which in European countries it is, at least on the last time I found a data set about it, then it could be that the storks bring the babies, it could be that the babies attract the storks, or it could be that there's something else that causes both of them. And this something else is usually related to things like economic development, etc. So the interesting thing now is for us working on this problem that all three of them lead to the same set of observable consequences. So the class of joint distributions that you can generate with any of these three models is the same. So if we have only these distributions, there's nothing. It seems like there's nothing we can do. So I'll talk a bit about this more during my talk. Now, maybe I should just very briefly mention, because so this is, here we have a graph where the confounder has arrows to X and Y. There's also an interesting setting where we have arrows to a third variable, X and Y, so now the arrows are pointing to Z. And this is Bergson's paradox, where you might start with two things. So here we have two correlated things that become independent by conditioning on a third variable. Here we start with two uncorrelated or independent things which become dependent by conditioning on a third variable, on a joint effect. And I think it's just important to know that this also can happen. So for instance, if you assume there's no correlation between whether someone is a good speaker and a good scientist, and if you further assume that there's a selection process going on, that in order to be successful as a scientist, you have to be good at least one of the two things. If you're bad at both, you're not going to make it. Then it turns out that among the successful scientists, there would be a negative correlation between being a good speaker and being a good scientist. So, but this was just a little parenthesis. Let's go back to this, to the Reichenbach principle. So basically, one can generalize Reichenbach's principle and build a nice theory of graphical causal models, which is was pioneered by Judea Pearl, Peter Swertes, and other people trying to connect computer science and causality and statistics. And in this theory, you have a set of, and some of you may have seen the tutorial 2 days ago. Maybe I can get a quick show of hands. How many have seen the causality tutorial? So I would say that's maybe 20%. So I'll very briefly for the others. So let's think of a model where we have a set of observables. We put them on a directed acyclic graph. The arrows in this graph represent direct causation. By this, we mean that each observable is nothing but a function of its direct causes, so the parents in the graph. So far, this is all deterministic. And a noise variable ui, u stands for unexplained. And we will assume that these noise variables are jointly independent, because if they weren't, we would refer back to the Reichenbach principle and say, oh, we have some correlation that needs to be explained. So there must be a joint cause for the dependent noise variables, which means that this system is not large enough. It doesn't capture all the interesting causality that's going on. So this is an assumption of what's called causal sufficiency. So if we specify now the distributions over the noise variables, then the whole thing implies an observational distribution, or so it implies a distribution which we call the observational distribution, joint distribution over all variables. And this distribution inherits some interesting properties from the topology of this graph. And it can be specified or captured in terms of the so-called causal Markov condition. So it turns out that this graph has particular conditional independence properties. And the graph, together with this observational distribution, is also called a graphical model. Now, what's interesting about this point of view on graphical models? So usually when people talk about graphical models, they will tell you about joint distributions and about conditionals, but not about these functions. Now, so this is a mechanistic point of view that tries to explain where the correlations come from in the first place. Nice thing about this framework is that it's trivial to model interventions. They simply correspond to changing functions. For instance, replacing one function with a constant means setting that variable to a constant. And then we can do the same thing. We can compute the distribution that's implied by it, and we get a different distribution, and then we have a distribution that corresponds to intervening on that variable. So that all follows directly. There's something called the do calculus of Perl, which basically you can derive yourself just from that one insight. Now, I won't go through this in detail. I just said a functional causal model implies the local causal Markov condition. So this is this conditional independence, without thinking about it in detail now. Turns out this local causal Markov condition also implies a global one that uses a graph theoretic notion called deseparation. The more important for us now in this talk is that it also implies a certain type of factorization of the joint probability distribution. So it turns out that if we have this graph, and if the dependencies are generated using these kinds of functions where each node depends only on its parents, then this implies that we can write the joint distribution as a product over conditionals where each conditional is conditioning only on the parents of that variable. So this is if you want, a much lower dimensional object. So this is a nice decomposition of the joint distribution, and it's a decomposition into terms that have a causal meaning in that they correspond to these mechanisms here that generate our dependencies. And of course, one important question in causality is when can we recover the graph from the joint distribution? So suppose we had infinite data from that joint distribution, but no interventions. We all know if we do interventions, we can learn about causality, but what if we can just observe? So what can we infer about the graph? And it turns out, while we usually cannot infer the graph, we can often at least, or we can, in the generic case, at least infer a class containing the correct graph by conditional independence testing, subject to some assumptions. And the idea for this is, so we have this graph, we put in our independent noises. You can think of them as probes, and as they spread through the graph, they pick up dependencies. So, and just by checking what depends on what through independence testing, conditional independence testing, you learn something about the graph structure. Now, there are some problems with this. One of them is that if these functions are complex, then conditional independence testing can be very hard. And the other problem is that it doesn't nail down the exact graph. And in particular, if you have only two variables, there are no conditional independencies. Conditional independence needs three quantities. And then the idea will be that the functions can also leave a footprint in the data that we can employ if we are willing to make certain assumptions about a certain type of independence, not of noise variables, but of mechanisms. And I'll talk about this. That's kind of the main point of this talk. So let's look at this two-variable case, which is also a classical problem philosophy. So Nietzsche called it reason's intrinsic form of corruption, so the error of mistaking cause for consequence. And let's look at one particular example just to convince you that in principle it might be possible to sometimes decide what is cause and what is effect. And this is a data set from the German Weather Service. So here we have the altitude of weather stations, and we have the average annual temperature. And you can see that the higher you go, the colder it gets on average. So Berlin is somewhere down here. So it's one of the warmer places in Germany, average, so 10 degrees Celsius average over the whole year, day and night. And we can now ask, does temperature cause altitude, in which case this would be the causal factorization, or does altitude cause temperature? So how would we go about it? Of course, we could try to intervene. So we could build a device to raise the measuring station by a few hundred meters, measure the temperature. Maybe we will find that the temperature then gets colder. So that might indicate that altitude causes temperature. We could also try the opposite experiment. We could try to build a big heating around a weather station and then measure the altitude, and the altitude won't change. So I think so in this case, even the thought experiment is already enough. So even a hypothetical intervention is enough. So we would expect if we intervene on the altitude, the temperature will change. And if we some introspection would probably tell you, well, it's plausible to think this will change because even though we might not know in detail or we might not remember our high school physics in detail, we would be willing to think there's a plausible physical mechanisms that, given an altitude, somehow produces a distribution over plausible temperatures for places with this altitude. And this mechanism should be independent of what altitudes we feed in. And also, similarly, we would expect that this mechanism might also be invariant across, for instance, different countries in a similar climate zone. So, a second example, maybe a little bit closer to neuroscience, or at least visual perception, is this one. So here we have this object called a Bechet chair. It's not a chair, as you can see. It consists of two pieces, and they are arranged such that if you look through this hole, you see a chair. So that means if you look through this hole, so in other words, if your perceptual process, in particular the viewing direction, is strongly dependent or picked based upon the object itself, then we see this chair. That means perception fails because we see something that's not there. Vice versa, I would argue that in the generic case, our perceptual system makes the assumption that the object, so that the cause of what we perceive, and our perceptual process, so the mechanism that turns this cause into a percept, are independent. It's also called the generic viewpoint assumption. And I think one can also connect it to the invariance idea. So if we look at an object, so you all know there's something called structure from motion. So even if you close one eye, you move the object, or you turn your head around the object, you can get an idea of the 3D structure of that object. And this also, of course, only works because we are assuming that as we move our head, the object itself doesn't change. So the object itself is invariant, and if this is the case, we can perform this inference. And of course, if this breaks, everything can go wrong. So, for instance, if you do something like if you wear some VR headsets, then they track your head position and show you something different, depending. That very much depends on your position of your head, etc. So then you create a dependence between the object and your perceptual process, and then again perception fails because you can see anything in a VR setup that has nothing to do with reality. So we can state this principle in words by saying that the causal generative process is composed of autonomous modules that do not inform or influence each other. So I've talked mostly about the influence. We also use this in some algorithms. One can formulate this more mathematically, but I also briefly want to say that these kinds of thoughts have been around for a long time. So in the early days of causality, people in economics, econometrics, thinking about structural equation modeling, etc., they were thinking about this kind of things already. So this is like most good ideas. This is not a new idea. So this, in various guises, has been around for a long time. So let's get back to this factorization. So what does our independence now mean? A little bit more mathematically, but still intuitive in this factorization. So we said this is our favorite way of representing a joint distribution. So in terms of the causal conditionals that generate and capture these dependencies. So we would then argue that a change in a real-world distribution always comes, of course, it must come from a change in at least one of the causal conditionals, if not many. We assume that these conditionals are independent, so if we change one of them, that in itself should not imply that the others have to change automatically. And I should say, if we write any other decomposition of the joint distribution into conditionals, there are many of them, then that will usually not hold. So usually one change will be combined with changes in others. Only in the causal factorization will it be reasonable to assume this independence of changes. So we would assume in reality, if we change a real system gradually into another one, then these changes should somehow be sparse or local in this factorization. Now let's go back to the special case of two variables and look at a particular simple example where we have so we have an input, so we have a cause with some distribution of the cause. We have a mechanism, in this case it's a mechanism without noise, and then we have the effect. And then what you can see in this picture is that this mechanism leaves a footprint leaves a footprint in the effect distribution, because wherever this mechanism was very flat, the effect distributions will be high, will have high density. So if input distribution and effect distribution are independent, then the same does not hold true for effect distribution and mechanism. So there's a dependence here. So this creates an asymmetry between a cause and effect, and one can formalize this. And there are different possible formalizations. One of them is written here. The details don't matter. But if we assume that a certain type of covariance vanishes in the forward direction, then we can prove that it's strictly positive in the backward direction. So that's maybe just the take-home message. At this point, one can analyze this in more details using information geometry. But I briefly want to mention so this is one example, or that this leads to a method to perform cause-effect inference by looking for this dependence between the mechanism and either this distribution or this distribution. And it turns out this actually works better than chance. So we've collected a number of data sets to do cause-effect inference, and then it turns out that these methods, so the chance level would basically mean you're in this gray area, but many of these methods actually stay outside that most of the time. And we've applied the same thing also to classify the direction of time, which is kind of a strange problem. Take a time series, decide whether it goes forward or backward. And also we can do the same thing for videos. This is just a little nice video here, which may have been in history the first time that people could see the direction of time, because this is a video from the Lumiere brothers, and they would operate the thing by hand. They turn the handle, they crank the handle, and then at some point they would start turning it backwards. So here now we're in the backwards area, and then you could see the wall coming up again. Yeah. So far I've talked about links between causal structure and statistical structures. But it's important to stress that the causal one is the fundamental one, because it captures the physical mechanism that generated the statistical dependencies in the first place. So the statistical structure, you could say, is just an epiphenomenon that follows if we make the unexplained variables, the noises, random. Now, we can do something different. Rather than making the unexplained variables random variables, we can instead make them independent bit strings, where we measure independence in terms of what's called algorithmic information. So we have a directed acyclic graph where we have a computer program, U, city on each node, running on a Turing machine, T, and taking as input the outputs of its parents, so the results of other programs running on the other nodes. And we assume that all programs are jointly independent, so all these unexplained things are jointly independent in the sense of Kolmogorov complexity, which simply means that a joint compression does not save space compared to individual compressions. And one can prove that this model implies a causal Markov condition, just like the statistical one. But we have to replace Shannon entropy with Kolmogorov complexity. And so we can get a whole theory of graphical models for this case also. And in principle, this one also applies for individual objects and not just statistical data. And so there's various things that are nice about this. And one particular thing that I like is then one can make an interesting connection to the thermodynamic arrow of time. So here's a little Gedanken experiment. We have a cause, a beam of particles flying in, then we have a mechanism that turns the cause into an effect. So the effect will be the particles flying out, and the mechanism will consist of scattering at this object. And this object, of course, has a non-trivial shape. And this photography, of course, works this way. We take a look at what's scattered by an object, we record it, and we infer something about the object from that. So certainly the effect contains information about the mechanism. The cause doesn't. The cause by assumption, the inflying lights, this highly ordered beam of particles, we will assume that this is independent of the shape of the object. And then it turns out that, so if we make this assumption that the incoming state and the mechanism of scattering are independent in the sense of algorithmic information. So again, joint compression does not save space. And then one can prove relatively straightforwardly that the Kolmogorov complexity of this thing under this time evolution, so after applying the scattering, is at least as large as before. So it's a non-decreasing quantity. In other words, if you accept Kolmogorov complexity as a measure of physical entropy, which some fundamental physicists do, then you get what's called the thermodynamic arrow of time, or the second law of thermodynamics. Okay, so one can also apply this independence principle to machine learning problems. And it's instructive to think about something that we usually don't do in machine learning, which is about, machine learning, we have inputs and outputs we predict. We don't care about whether the inputs are causes or effects or whether they're confounded. And in a deep sense, we don't need to care about this as long as we are in an IID setting. But once things get more complicated, it's interesting to care about that. And the first level of complexity would be to say, let's just distinguish two cases, causal and anti-causals. Causal means prediction is aligned with causality, and anti-causal means the prediction is opposite direction of the causation. And it turns out, so now we make our assumption that the mechanisms are independent, which in the two-variable case simply means that the input distribution and the conditional of effect given cause, so the cause distribution and conditional of effect given cause, are independent. So these are our two mechanisms now. And now for causal learning and anti-causal, this implies different things. And so let me talk about the causal one first. So in the causal case, this implies that these two objects are independent. Now, if we think about what do we usually do in machine learning is about estimating some aspects of this quantity. If we do regression estimation, we just estimate the expectation of this. If we do classification, we estimate whether this thing is larger than 50% or something like that. So we're interested in this quantity here. Now, if these two objects are independent, that means just seeing inputs without labels should not tell us anything about this conditional. But that's what semi-supervised learning is trying to do. So in semi-supervised learning, we are asking the question, what if we have additional inputs? What if we know more about this? How can we improve our estimate of this? So the prediction would be in the causal setting, semi-supervised learning should be impossible. And by the same kind of argument in the anti-causal direction, it should be in principle possible. if we are remembering this argument from before, that if we assume independence in the forward direction, we get strict dependence in the backward direction. And it turns out, just by a meta-analysis of benchmarks that other people have run, this is exactly what we observe. So this was a nice confirmation, and actually it's also closely related to various assumptions that people have made for semi-supervised learning. And we can generalize this, which we've recently done, to a case where we predict a target from both causal and effect features. And this then leads us to a sort of a higher order type of semi-supervised learning, where we talk about, not about a cluster assumption, but about a conditional cluster assumption. But I think I won't have time to go into that. So I'm quite interested in exploiting or in learning this kind of structured models, so learning models for joint distributions where certain components are robust, are causal, are transferable. And one first step in this direction was, for us, was this paper that we published last year. So here we have some digits. We all like handwritten digits, and then we distort them with various types of perturbations, like adding noise, inverting them, shifting them around in the image. And then we came up with a model that takes as input distorted images and normal images, but we don't tell the system what kind of distortions have been applied. We also don't tell them the digit class, so they just get these distorted images, normal images, and then it's a bit like a gun, only in a more modular way. So this is basically a gun which, using a set of different experts, generates from a distorted image, tries to generate realistic images, and then the discriminator checks how realistic these images are compared to the real data set. And then it works by a competition, so these experts compete, these modules compete for the data, and then they will gradually end up specializing on different transformations. So through the training process, we will get experts specializing on left translation, up translation, inverting digits, denoising them, etc. And then we feed in random distorted images, and the system always decides automatically which expert to apply and how to change the digit, and it does so also. It can do the same thing also for other types of digits. So it really has learned these transformations in a reasonably robust way. And currently what we're working on is a system that in a way takes this to the next step, and does it in a recurrent setting. So we're trying to learn recurrent mechanisms that communicate sparsely and can do various things based on that. But I think I'm going to skip through that quickly, because I have something interesting at the end, which probably will come as a surprise. So I want to get to that. This is another thing that goes in this direction, where we are trying to combine multiple representations of different examples in a reasonably causally meaningful way to generate new images, and we can use this to also generate hybrids of images. So where we start with this one and this one, and then we hybridize them in the hidden representation, and end up with these maybe also slightly creepy-looking things. So this is a teddy bear. That's a real koala. This looks a bit like a koala teddy bear, or this also looks a little bit funny. So yes. So I think I have about five or 10 minutes left. Okay, super. Good. So. Overall, I think of things as a continuum of different levels of detail in modeling. So we have statistical models, which we all like because we can learn them from data. This is the data-driven paradigm. And we know we can use them to do IID prediction, pattern recognition. We speak about things like generalizations. And generalizations in this case simply means given a new point that's sampled from the same distribution. So some people would claim this is interpolation. Judea Pearl would claim this is just curve fitting. But there's a whole theory of this statistical learning theory that calls it generalization, and it's a non-trivial theory. So I would I would argue there's a lot of merit in studying this problem. Then the next harder problem is predict under shift and intervention. That means generalizing to other problems. Purely statistical models are stuffed already here. They also don't provide physical insight. They don't let us think or reason. And here my favorite quotation is this definition of thinking due to Konrad Lorenz, who once said thinking is nothing but acting in an imagined space. Now, at the other extreme, if the gold standard of modeling for physicists is a set of coupled differential equations. In principle, with that you can do anything, but we don't have good methods to learn these from data. Now, this field of causal learning is trying to somehow stay in between. We would like to be able to learn as much as possible from data. And if we can do that, then we would get richer models that can do that statistical ones can't do. So we want to be able to predict also under shifts and interventions, and we want to get some physical insight. And ideally, we would also like to have models that sort of go beyond the current deep learning hype, which is all about getting statistical representations of data, or which is mostly about getting statistical representations of data, and move towards representations that allow us to act in an imagined space. So the hope would be to, and this is, again, this is quite close to what Nando is now also working on, to learn multitask, multi-environment models where we have a finite-sized brain that has to solve a lot of different problems, that doesn't want to start from scratch and retrain on a huge IID data set every time a new problem comes around. And if we do that, then I think necessarily it will have to use components that are robust across tasks. And from my point of view, these would be causal components. That would give us then this kind of representation learning that goes in the direction of Konrad Lorenz. Now, I want to, at the end, show you one particular application of a causal model, which is of particular current interest. I mean, you've all read the news recently about the exoplanets, and this is an application to the Kepler Space Telescope data. So Kepler has been staring at one patch of Milky Way for several years, looking for these slight changes in brightness of stars that occur when a planet passes through the line of sight between a star and us. Now, this is not so likely if you go out into space and you want to see that happening. If this planet were the Earth and this is our sun, you would have a 0.5% chance to be in the right direction so that things align and you can see it. But Kepler looks at several 100,000 stars, so there should be quite a few that might have this kind of alignment if they have planets. And sure enough, Kepler has found quite a few planets. Now, the problem from a data analysis point of view is non-trivial because we have the astrophysical signal, and then we get these measurements, but the measurements are not just influenced by this signal, but also by the telescope. In particular, the pointing of the telescope is non-trivial. It's a very subtle thing. It even has to correct for the radiation pressure of the solar radiation. And nevertheless, you can see that here we have a set of pixels that all measure the same star over 3 months. You can see that some of them get fainter, others get brighter, and that points at slight variations. So the star is moving a little bit across the CCD. Now, interestingly, if we look at a completely different star, it's probably light years away from this one, we can see some shared behavior. So we can see, also this one seems to be, the left pixels are getting darker, the right ones are getting brighter. Now, how can these two things share information if they're light years apart? They can only share information if they're influenced by the same quantity, and that's the telescope. So now the idea is to improve our estimate for this thing by taking into account whatever we can predict from here, because whatever we can predict in Y based on X can only be due to this shared noise source. So we'll try to perform a regression of Y on X and see what that brings us. And the intuition can be also visualized with this thing, which we've called the Milkman Problem. So here we have a set of children, all children of the same mother. And you know that sometimes not everybody knows their biological father, and some people claim that it's up to 20% of the people who don't. So here we have, and please not to be taken too seriously, so here we have a set of children, and the Milkman problem now is not to find whose child is the milkman's, but it's to find out how does the milkman look without seeing the milkman. So we only see the children, we don't even see the mother, but we want to infer how the milkman looks. And the way we do it is we will sort of regress each child upon the others, so predict the appearance of the children based on the others, and then sort of remove that, and whatever is left after explaining this child in terms of the others will be the milkman. And I think it's an interesting method, so it could also be interesting for neuroscience applications. And if we're willing to make some assumptions, in particular a certain type of additivity assumptions, then we can actually prove. So we assume this additive, so-called additive noise model, which is something that was studied a lot in causality over the last years. And we assume that in principle, all the information there is about the effect of the noise on the observation, in principle, could be predicted from the other stars without knowing how. We don't need to know this function phi. If we assume this, then it turns out, and it's almost too good to be true, that if we subtract the regression of y on x from the observation y, then what we get is the original signal q, the astrophysical signal, up to an offset. And this is an equality of random variables, so it's almost surely. So this is quite surprising. We can also generalize it to a setting where we delete this assumption, then we get a slightly weaker statement. Anyway, if we do this, we can take the original light curves and we process them to get this kind of thing where we nicely see these little transits, and it looks much nicer than what the astronomers using their traditional methods got before. And so that was all nice. We did that a few years ago. But then what happened while we were working on this was initially bad news for Kepler, but it turned out good news for us that so two of the reaction wheels, Kepler had 4 reaction wheels that can rotate and help stabilize this thing in space. 2 of them broke, and it had 4, so there was some redundancy, but with only 2 left, it couldn't orient itself anymore. And so they were close to giving up, and then some people came up with the idea of at least using the remaining fuel. So they combined the fuel thrusters with the 2 wheels and sort of reasonably stabilized it and looked at some other patches of Milky Way. And that was, and they could only do it in certain directions, which were computed based on the shape of the spacecraft. So they could come up with a few patches along the ecliptic, so in the ecliptic plane, and produce, of course, much more noisy data. Control was not so good anymore, but that was good for us because we knew we had a good method to deal with noise. So we immediately looked at the data and produced a set of planet candidates that we thought, from our point of view, and I should say the model was a little bit more sophisticated than what I just showed, in that it was not just fitting the noise in terms of the other stars, but in addition fitting a transit shape. So we came up with a set of around 30 candidates, one of them down here. Now, these 30 candidates were then, a few months later, in another paper, people looked at them in more detail, and sure enough, they confirmed about half of them. There were a few false positives, and the rest were still open. But this one that I marked before was confirmed. And what was nice about this planet was that it was lying. So here, if you look at the temperature in Kelvin, 272 degrees, plus minus 15, that's a reasonable temperature for liquid water. So that was an interesting planet. It was in the habitable zone. So not too hot, not too cold, but nice and temperate. And then just a few days ago, on Wednesday or Thursday, there was this news that people found water vapor on this planet K2-18b, and actually I first thought that's nice, but then I got an email from my collaborator in New York. He said, well, did you notice this is actually one of the planets that we discovered? So that was quite nice, and this is now a big thing in astronomy. It's the first habitable zone planet with proof of water vapor in the atmosphere, and it's I had to check where it is, and it lies. This is, for those into astronomy, this is Leo, the constellation, and here it's too faint, you don't see it. In this box is our planet. This is Sun, Mars, Venus, and Mercury. So all the inner planets in the Sun are exactly in this direction. Seems like a cosmic coincidence that we find it right now. Or that is published right now. Actually, it was published based on data that was done some years ago. So that's a nice implication of machine learning and causal modeling applied to astronomy. And with that, I would like to thank you for your attention.
Okay, we have time for a question or two while the next speaker comes down and sets up their computer.
Okay, hey.
Are you gonna
Thanks for great overview. I'm right here, maybe
Okay.
confused because of the sound. Yes, so I have an immediate question to the last slide. What is the Death Star black hole? It was on the list. But that is maybe afterwards. So, so do you? I'm just curious. Do you see any link between using interventions for causal interference and the way how this class of models called generative adversarial networks are doing well? So it seems that just by using a generator there, in an adversarial way, you can discover variables in latent space that cause the image observables to be so. And it seems to work with quite little supervision. You just try to trick out a discriminator, so generator does interventions, I think, in this sense, to do this. Do you see there any connection? I would like to have your take on this.
Yeah, I mean, so if you speak about it like that, that means you are considering this neural network as an artifact or as a mechanism that produces, so then the neural network itself is a causal agent. And I think this kind of point of view can be useful. It's also applied by some people when they speak about counterfactual manipulations of inputs in order to generate to analyze systems in terms of their interpretability. So it's like I say, it's not the standard way of thinking about it, but I think it could be fruitful. Yeah.
move on to our contributed talk? Let's thank Bernhard one more time.